Hello, my name is Oscar Real. I'm a PhD student from Mexico and I'm going to present you our work which is titled Obtaining Object Information from a Stereo Vision System for Autonomous Vehicles. Autonomous navigation is a task that requires the most information it can get from its surroundings for safety, accuracy, and decision making. In our work, we present a stereo vision system capable of obtaining object information for autonomous vehicles. Advanced driver assistance systems have also been proposed to increase safety as an assistance for drivers or self-driving cars. For example, on this work, a vision-based advanced driver assistance system for forward vehicle detection using convolutional neural networks and motion tracking is presented. Also, on this other work, the authors present a vision based on system for driving assistance, which purpose is to avoid potential traffic accidents due to forward collision and vehicle overtaking and assistance to perform safe lane change operations. Both of these works make use of object detection algorithms to perform their task. The difference with our proposal is that the aim of our work is to provide information about multiple objects of interest using object detection and stereo vision, which is more accurate to provide depth estimation. The stereo vision system is merged with an object detection algorithm to carry out this task. The merge between these systems is a proposal to create a vision system for autonomous navigation tasks that provides information about objects of interest in the field of view, such as object description, distance, height, and width. This block diagram presents the steps to calculate this information. The first step is to calibrate the cameras if needed. If it doesn't need calibration, the next step will be to capture the stereo images. Then, the object detection algorithm will get the coordinates of objects on the images. Then, a pattern match algorithm will find this object in the second image. The coordinates of these objects will be converted to angles, and this information will be used to triangulate the object's world position with the object image's positions to obtain the distance of the object from the vision system. Then, the distance information, the width and length of the object can be calculated converting the pixels width and length to real-world distances since the distance of the object is known. After the system provides the information such as object description, width, length, and distance, the process can be repeated from the capture stereo image steps for a real-time application. The camera calibration method for a proposed vision system is as in our past work, where the developed stereo vision system performs the camera calibration method, high-speed pattern recognition feature, and triangulation process to obtain the 3D point coordinates. This calibration method uses the least squared technique to optimize the function and compensate the error generated by the lens distortion. This calibration method was selected because it is developed specifically for stereo vision systems with the purpose of locating 3D points without estimating intrinsic or extrinsic parameters with low computational cost. The camera calibration method consists in 4 steps. The first step is to estimate the horizontal and vertical angles for each of the intersections between squares of the calibration pattern. The second step is to use the stereo vision system to estimate the same horizontal and vertical angles with the information given by the cameras over the calibration pattern. The third step is to find the adjustment angles using the least squares method. The final step is to adjust the angles obtained by the stereo vision system by adding the difference given by the least square method. After the stereo vision system acquires the pair of stereo images, the objects of interest need to be identified in the left image using the detection algorithm, and then matched with the corresponding pair on the other image using a pattern match algorithm. Object detection is a computer vision technique that allows us to identify and locate objects in an image or video. With this kind of identification and localization, object detection can be used to count objects in a scene, determine and track their precise locations, all while accurately labeling them. The object detection algorithm is the most demanding of the methods on the proposed system in terms of speed and computational processing. The object match algorithm is based on a pattern match algorithm, which is a method where a correlation window of brightness pattern is performed between a template of the source image and the image target. Then, the algorithm provides regions of the image target that has the most corresponding brightness with respect to the image template. The task of the object match algorithm is to use the coordinates of every object given by the object detection algorithm and find their matching object coordinates. For example, the objects are detected on the left image and their corresponding match is found on the right image by using a template image of the object on the left image. As you can see on the card, there is a red box which is the image template taken from the car. This template is used to find the match on the right image, which is shown also in a red box connected to the template by a red line. This principle is also applied to the other objects, as you can see on the bicycle and the person. The triangulation step for the proposed system is based on the dynamic triangulation equations for laser scanner. It is performed with the baseline of the cameras and the object of interest in each image. In order to apply these equations with the information given by the object detection and object match algorithms, the pixel coordinates of the objects of interest must be converted to angles, where the pixels of each 3D point projections on the pair images estimated in the pattern match are used to calculate the angles. Once the pixel coordinates of the objects are converted to angles, the triangulation equations can be used to calculate the real-world object coordinates. Once the distance of the object is known, the relationship between the distance and the object's width and length in pixels can be used to calculate the real-world width and length of the object. This is our proposed prototype for a system. It comes with two USB cameras with a varifocal lens between 5 and 50 mm and a Sony ISIE2021 sensor. These cameras are connected to a laptop running on Windows 10 with an Intel Core i7 processor at 2.5 GHz. And the cameras are positioned in a stereo geometry of a coplanar camera system with a separation of 100 mm and a height of 950 mm. The software for the proposed prototype is still in development and some steps of the methodology are executed separately. The stereo images are taken on the main program. Then the left image is used on the object detection algorithm mask RCNN image segmentation demo with the Google Colab tools. This algorithm returns the left image with overlaid boxes, instances masks, and labels of the detected objects. Then, the center of overlaid boxes are used on the main program as a template pattern to find on the right image. After every match is obtained, the triangulation process starts to obtain the object distance and then the width and height can be calculated. Here we have an example of the developed experiment. On image A, there is a pair of captured stereo images where there is a person crossing the street at almost 4 meters from the vision system. On image B, the object detection algorithm returning the left image with an overlaid box, instance mask, and a label for the person with a 99% of certainty. Image C shows the object match on the right image, which is performed by selecting a template pattern from the center of the object detected on the left image, and then this pattern is found on the right image. On the experiment results, the object detection algorithm predicted correctly that the object of interest was a person. The measured distance calculated by the system is 3961 mm and compared to a real distance which is 3850 mm measured with a laser distance meter, the distance error is 111 mm. The measured height is 1811.21 mm with an error of 5.21 mm, and the measured width is 538.21 mm. To test our methodology, real-world images for the intended application were used. These images show 5 experiments performed in different scenes. In every scene, there is an object that the algorithm must detect, labeled as a person, and give the distance, height, and width. This table shows the results of the performed experiments. The object detection algorithm predicted correctly that the object of interest was a person with 99% of certainty. The distance error was plus minus 91.5 mm. The height error is plus minus 23.365 mm. And the width value can be compared with the real value because it changes as the object moves and the ends of the object expand or retract. In conclusion, we presented a stereo vision system for autonomous vehicles capable of obtaining information about the objects in the field of view, such as description, distance, width, and height. As it can be seen from the results of the experiment, the system does a good work for providing this information, but there's still room for improvement, specifically on the distance calculation. For future work, the next steps are to implement the object detection algorithm and a stereo vision in an embedded system, in order to provide the information in real time to an autonomous vehicle. Also, we're working on a fast pattern match algorithm for stereo images to increase the frames per second processed by the system. That's all for my part. Thanks for your attention.